for example, how to do a straight line or anything like this. بس السؤال الأول طبعا accuracy. How much accurate you should be when you solve your problem في الامتحان. طبعا accuracy ما we don't expect يعني إن خصوصا لما أي شيء involves drawing، فما تتوقع أنك أنت you will get exact numbers. بس أيضا المفروض ما يكونش الفارق كبير جدا. For example لو مثلا النمبر في stages مثلا 8 or for example 7، المفروض الإجابة تتراوح ما بين الرقم 8 for example. ممكن يعني طالب يحسبها يلاقيها مثلا 9، طالب ثاني يحسبها 7، طالب ثاني يحسبها 8 أو 7 point something. فأنت عندك range يعني في number of stages. احنا أيضا لما when we mark the paper we usually try to see where exactly the error is. يعني إذا كان في مثلا significant difference، أنت you got your answer. Let's say for example أنت المفروض the number of stages was supposed to be 8 and you counted number of stages and you find the number of stages to be for example 3 or 4 or 5. So now here we are talking about 50% difference. Not even 50%, it's almost 100% difference. In this case, you will have, we usually what we do, we go back and see what exactly was wrong with your لأن مستحيل هيكون الخطأ في العد، مستحيل الطالب يغلط في العد يعني. You're going to draw just straight line and you try to connect them. Very simple. It should be very simple. Okay, don't worry that much. As long as your answer close to the real answer, you should be okay. We don't expect to get exact numbers, but at the same time, you shouldn't also deviate or have a significant difference from the answer that's supposed to be done. Okay, so this is regarding the accuracy or how much accurate you should be when you answer any question involving drawing, involving graphical solution, of course. Today we will try to solve this example, which is already in your slides, I guess. And as you see here, a saturated vapor mixture of A and B. So regardless of the components A and B, but main issue is binary system, because the Bunsen-Savarite method and Mercaptan method, we are using, they are used for binary system. So you have A and B components to be separated using continuous distillation column. So you have a continuous distillation column. Let's assume this is your distillation column. So this is your feed, and this is your condenser, and this is your partial reborder. And as I said before, usually we have partial reborders in most applications. And these are the stages that we try to determine. Okay. So I have A and B. Usually I write the composition of the more volatile component using a continuous. The feed contains 50% of the more volatile component. So I have Z here is equal ZF or XF, doesn't matter. It's basically 0.5. Okay. And the bottom product contains 4 mol%. So XW here X is equal to 0.4. Sorry, 0.04, not 0.4. You see here where the mistake can be. So 0.04. And the bottom, the distillate contains 95%. So you have, this is D, and this is your F here, and this is your, let's say W, if you want to call it W, and XT here is 0.95. Using Bunsen-Savarite method, so we have to involve the material and energy and equilibrium equations, material balance equations. and determine the number of theoretical stages. So we said theoretical stages means you are determining the theoretical stages, and that means they are at equilibrium. In each stage, the vapor and the liquid leaving that stage must be at equilibrium. Needed for this process, their flux ratio is 1.5. So one of the information you are given here, that your flux ratio here is equal to 1.75 flux ratio minimum. So once you see this one, that means you have to determine R minimum first. And the average of the volatility is going to be, or is given to be 5. So these are the information given. And then all what you have to do is just try to, as I said here, in order to do the solution or to solve the problem, you have to use the general equation, if you remember that, and the of the column, the top column and the bottom column. But before all of that, you have to draw the equilibrium data. I'm not sure if you remember the equation of the equilibrium data or not, but usually this is basically alpha A B is equal to YA, let's say YA over XA over 1 minus YA over 1 minus XA. And therefore you have two unknowns in this equation, and then you will have to generate the data. We will see how we do that. But first of all, we have to determine the values of W and D. We don't know this one, we don't know this one. So now, according to the degrees of freedom, we have 3 unknowns, F, D, W, and we have only 2 equations that we can use, independent equations. So therefore, we have to we have to specify the basis. So we have to identify the bases, and we say gonna be, let's say, assuming this one is any 100. Okay. Kilogram mole. We usually write kilomole. Per hour, and based on that, we will solve the problem. Now we have the first equation, says 100 is equal to dZW. The other equation is going to be for the component, more volatile component, so it's going to be 50 here, because 0.5 multiplied by 100 is going to be 50. It's going to be 0.95 D plus 0. So now if I solve these 2 equations simultaneously, I'm not sure if I want to spend time to, or waste your time to solve these 2 equations. This one is very straightforward, and I think it's okay. And should we go through the solution of these 2 equations, guys? Don't you think it's okay if we go quickly here and we give the answer? Because I think this one is not.
No, it's okay.
I think no need.
No need. So we don't have to waste time. So if you do these calculations, you can review it and you have the answer. You will be able to find out that D is equal to, I think as it's written in your slides, 50 kilomole per hour, and W should be 100 minus, so it's going to be 49. Oh, you can, for your just information, 49.45. You can go and check it when you have time, maybe. Just double check. So I have now D, W, and everything. Okay, now we come to the next step, which is going to be determining the R minimum. How are we going to be able to determine R minimum? I need to use make-up-tail method, because there is also another method that you can use to determine R minimum by using the Bunch and Savaritis graph, but it will give you almost the same answer. So there is no need to waste your time on that approach. So we will stick to the approach used by make-up-tail method. So now, in order to be able to do that, we'll have to generate the equilibrium data. Generate the equilibrium data means you're going to basically you'll use this squeeze. So you're going to say this one here. You will say this is y over x here, okay, and this is going to be multiplied by 1 minus x here over 1 minus y. This is going to be 5. If you try to say y 1 minus x here is equal to 5x minus 5y. Okay, so if you I don't know how to do that, but you can say y it's going to be 1 minus x here, because this is going to be plus 5. It's going to be 5x. So you can have an equation that says it's going to be 5x over 1 minus x plus 5. So this equation will be used to generate this table here, and this table is going to start from 0, for example, as it is written here, 0.1, it's up to you, 0.2, 0.3 here, and you go down 0.4, 0.5, maybe don't have to 0.6, 0.8, 0.9, and 1. So now if I put yx is equal to 0, so I will use this equation. When x is equal to 0, y is going to be 0, and when x is equal to 1, y is going to be 1. You can check that. Now, but what about if x is equal to 0.1? How much is the answer? So y at x is equal to 0.1, I'll give you 1 at this 1 point, is going to be 5 multiplied by 0.1 over 1 minus 0.1 plus 5. So if I do that, should be able to get it. Try my phone calculator here, hopefully it will work. Okay, so it's going to be, what's that? 0.5 divided by, I'll use scientific, can you help me guys here? Divided by, what was it going to be?
0.08.
So probably we're using different equations here. Can you check the equation, because I have different numbers to be honest.
0.085.
This one is 0.0?
Yeah, 0.085.
Okay. I have different numbers here. Why is that? When I did the calculation, I got different numbers here.
I got the same answer.
Yeah, probably I wrote the equation completely different here. Let me check this one here. Can you check this equation here? Maybe I wrote this equation wrong because I got different values, to be honest. 1 minus, let me see here. 1 minus x plus 5. This one is going to be here. Is going to 5x. And this is going to be, probably I made a mistake here. If I do here that again, so you're going to have y 1 minus x plus 5y. Just to confirm what I'm doing is correct here. Is equal to 5x. I'm not sure this equation is right, to be honest. I think it is wrong here. Should be, I guess it should be alpha multiplied by x, which is okay, divided by 1 plus. So there is a problem with this equation. I think I got this one wrong here. The equation that I made a mistake in the derivation. So can you just please, we try later on, try to write the equation, the one that we have in the slides. So it is basically, should be, this equation should be like this one. This one, y, sorry.
So 5xy maybe.
Yeah, can you check 5 multiplied alpha, which is alpha. This is the equation that I use. Alpha multiplied by x divided by 1 plus alpha minus 1 multiplied by x. Can you try this one now? Alpha is 5, x over 1 plus, you see here, this is the problem, I guess. 1 plus 4x. Now, if I put this one now, can you try this now and try to substitute 0.5? What will happen? So if y at 0.5, 0.1, so going to be 5 multiplied by 0.1 divided by 1 plus 0.4. Can you check this one?
0.35.
0.36.
Yeah, this one is right. I got, because I think the one that I wrote previously wasn't right. Yeah, 0.357, yes. So exactly right. Now this equation that 0.357 or something like this. So this is 0.357. What about the other 1.2 when we have this 1.2?
Point 556.
0.5.
Yes, and one is 0.3.
0.682.
And one 0.4 at 0.4.
0.77.
0.77.
And that 0.5 is going to be
0.833.
0.6 here.
0.88.
And 0.8 is going to be what?
0.921. 921.
0.9 to
21.
there at 0.9 is going to be 0.9 something.
0.978.
Okay, now this is the first line you have to draw, and you have to go to this, the diagram here, and you have x's. This is your x's here, and this is your y. And you have to locate these points. So this is the first point you have, and you have to be as accurate as possible here. And this is the last point here, where it is going to represent y11 and x11. Then the other one, try to make sure you got right. Now at point 1, we have 0.35. So 0.35 is going to be somewhere here. Here you have to be careful when you read the scale. So here it's 3, and then 3, 2, 3, 4. So 3, 5, 7, let's go 3, 6. So 3, 2, 4, 6. So it's going to be here, approximately. And then at 0.255, 0.2, you're going to go up here, 0.55, let's say here. 2, 4, somewhere here. And here why we have sometimes issues with the scale, so you gotta be careful. At 0.3 is gonna be 0.68. 0.68 is gonna be 0.67, 2, 468. So it's gonna be somewhere here. 0.4, 0.77. 4, 6 here. And then 0.5 is gonna 833. In
Doctor,
some
you
cases you
0.7.
sorry.
You missed 0.7 the x values.
That doesn't have to be all the points, by the way, because at the end of the day, you're going to connect them together. You don't have to do, but for example, if it was like in the exam, I would have used only 0 and 0.2, 0.4, 0.6, 0.8, and that's it, because you have to be fast. Okay, so because at the end of the day, you're going to connect it anyway. Okay, so at 0.5, we have 0.833, so 0.833 is going to be here too, yeah, somewhere here. And 0.6, 0.88, and this 0.8 and is somewhere here. 0.9 is going to be 0.97. Sorry, what I did here. Where's my 0.8? 0.6, it is 0.8 is 0.92. This is 92 here. And at 0.9 is going to 0.97, so 9. This is 2, 4, 6, 7. And this is the last point. So now we try to connect them easily. So I will go straight like this one. Sorry about this one, it wasn't really good. So sometimes you have to repeat the drawing here. This area is not clear here. Somehow, yani, not really what we're expecting, but I think we have to throw it a little bit. See, when you draw on the computer, sometimes not really. So 0.97 here.
Doctor, because 0.8, 0.95.
Sorry?
Because the value of 0.8 is wrong and 0.9 is wrong as well.
Really?
Yeah, 0.80, 0.95 and
No, just a
0.90.
moment. So this one, you mean this one is wrong?
Yes.
What is the value here should be? Point what?
95.
Okay, 9. And any other points are wrong?
Yeah, 9.9, 0.98.
What is the value of the 0.9?
Yeah.
0.9 should be 0.9?
8.
78,
98, yes.
like this one.
Yeah.
So this one is 0.95, so it's going to be here. 2, 4, so this one is going to be here. And 0.9 is 0.98, 6, so it's going to be here. I will try my best now. Hopefully it's going to work here. Yeah, okay, good. We don't have to forget to draw this line, by the way. So we have to draw the diagonal line that will help us counting. When we're going to count, my best, I'll try my best again here. It's going to be somewhere here. So this is my, let's say, this is my diagonal line, and this is my equilibrium curve. And now I have to go back and see where exactly my XD. XD is here. This is my XD is 0.95, and this is my XW. This is my X feed. So I go here, and they say this is my 0.95 here. Okay, 0.95. That means it is just here. It is 0.95246. So it's going to be here. This is my XD, and I have to use this one. So this is exactly where I should have the first line. And my x feed is 0.5, so it's going to be here. There's no need to use the ruler. This is my x feed. This is my xd. xw is 0.04. I don't need xw because I want just to determine the minimum. But I need to know the condition of the feed. The condition of the feed, he says what? If you go back to the problem, he says saturated vapor mixture. Saturated vapor mixture means Q is equal to what here?
0.
Yeah, so 0. Q is equal to 0. That means the slope should be what? Slope of the Q line. Do you remember the Q line? It's equal to Q over Q minus 1 x plus minus, sorry, x feed over Q minus 1. So the slope here, this one is 0. The slope is 0. That means it's going to be horizontal. So all I have to do is just to draw a horizontal line here. Okay, so I take this ruler, flip it around, sorry, I'm new in this technology, try my best. Yeah, I got here. That's it, that's my line here. A little bit, okay. Oops, easy. Why is not working? Yep, so I go and just draw a line, any line. Now, why am I drawing this line here? Because I want to determine the minimum, R minimum. So what I'll do, I start from this point here and try to connect it to this point, because this one is going to give me the pinch, and I extend it to get the value that I'm looking for here, approximately here. So that my value is going to be, that will help me to determine the intercept here. So what is the value of the intercept here from the graph is going to be what?
0.41.
Yeah. If I was in the exam, I will say this one is 0.4. I don't have to try, because what you have in the slides is because it is extracted from the Excel sheet. So if you say it's going to be 0.4 here, now you know what is this 0.4 representing. You go back to the equation of the operating line. So we know the operating line is what? It's basically y. This is for the operating line. The top section is basically r over r plus 1, صح? X plus xd over r plus 1. So if you compare this one, at x is equal 0, y should be what? Should be xd over r plus 1. Now you know what is this value is from the graph is equal to 0.4. So that means r plus 1, since it is minimum here. Why it is minimum? Because this separating line crosses this equilibrium curve, my Q line here, okay? So this R minimum plus 1 is equal to XD over 0.4. Now that means X minimum is equal to XD over 4 minus 1. Now I know XD is 0.95, so 0.95 over 0.4 minus 1. So what is the value now R for R minimum? So what is the value of 0.94?
1.375.
1.3. Let's say 1.3 is enough. So therefore, now my R, actual R, that I'm going to use is going to be what he says here. It is in 1.755 minimum. So this is given in the statement here. So all what I have to do is go and try to say 1.75 R minimum, which means it's going to be 1.75 multiplied by 1.3. So now that will be what?
2.27.
2.27. 27, let's say 2.3. So now this is the value that I'm going to use now in the Poisson-Savarite method to determine the number of stages. So all what we did so far is just to determine this value. Is this clear?
Yes.
So now you see the accuracy, even when you draw, you should get, not exact numbers, but at least close to the numbers that you get when you use the Excel sheet. Okay, as long as you don't have any mistakes, and you see mistakes can happen. You see what we did here when we wrote the equation completely wrong, and we only realized that because I have the answer. I know the answer from the drawing. I know it shouldn't be like this, but things can go wrong anytime, and you have to be careful. Now we are finished with the R minimum. Now we have to go and start solving determining the number of stages. Okay, now the number of stages here, as you see, we will use Poisson-Savarite method. So now I know, let me go back to this drawing. And I will take this one down here because I need it down. Okay, so what I do, okay, so we'll start with the first equation because I need to, these are, let's say, this is your scale. So maybe this one is going to be 0 here, and this is your x and y. And you start from 0 to 1, okay? So maybe you'll say this is going to be 0.1, 0.2, 0.3, and so on, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. Clear. So now the scale here within this, each one is going to be 0.9, for example, this one here. It's going to be 0.92, 0.94, 0.96, 0.98, and so on. So you know the scale inside the small scale, the major scale, and the minor scales. Now we have to determine a few points here, and the first one is going to be OD. Okay. I know from the equations that we derived, R is equal to OD minus H1 over H1 minus H small 0. Now if I go back to the equations here, to the example, I think he gave you the enthalpy as a function of composition. So this is the enthalpy of saturated vapor. So this is going to be H capital as a function of Y. The other one is saturated liquid, so it's going to be H small as a function of X. So I have to write these equations. I need them. I go here and say, okay, I have two equations given to me. Says for any saturated vapor, H can be calculated as a function of the composition, and it is equal to 67, I think, 0.63 minus 24.9 Y, and this is also this one is going to be what, kilojoule per mole, and H small as a function of X is basically 30.48 minus 18.8 x here, and this is also going to be kilojoule per mole. Now these are straight lines. So now either you have the data of the enthalpy as a function of composition in table, as we did for the previous example, or sometimes it's given as a function. So now if I want to draw these 2 points here, or these two graphs here, I will say, okay, now I can draw this one in this range from 0 to 1. So now I can say h capital, to start with the big number here. So h at y is equal 0 is equal to what here? 67.
67.
Yes, 67.63. And h, of course, going to be at y is equal 1 is going to be what? 67 minus 24. How much is going to be the value? Can you do it for me? 67.63 minus 24.9.
42.7.
42.7. And h at x equals 0 is going to be 30.48. Again, kilojoule per mole. And h at x equal 1 is going to be 30 minus 18. How much is the value? Okay, it is going to be 7. I don't know. 6 here.
11.67.
So
11.67.
11.
Yes.
So this is going to be also kilojoule per mole. But now here I can start. I don't have the scale here. I don't have nothing here. Now, and this is the trick here. And most of the equations, or sorry, most of the problems that you're going to solve using Python supply, how you adjust the scale, how much big or how much size you need to draw your paper. So you have a graph paper, and sometimes you select here, maybe you say here we have 10, 20, 30, 40, maybe until you reach here, you will not be able to reach this maximum value. But now if I ask you, what is going to be the maximum value in this graph should be? If I ask you, what do you think the maximum value is going to be? Now you have to put this in mind. You remember when we said function separate, we are talking about something like this one. We're going to talk about this curve, this small curve, and we have something called OD here. So OD is going to be the maximum value in this graph. So it's not going to be this value or this value. The maximum is going to be OD. So I have to make sure I include OD in my scale. So before I start scaling, putting numbers here, I'll have to check first of all what's OD first, and then I can compare it, and I can be 100% sure it's going to be okay. My graph will be okay. So now how I'm going to be able to determine OD? I have to go back to this equation. I need H1 and I need H small 0 here. How we calculate H1, guys? How are we going to be able to calculate H1? Do you know? What's H1? What's the meaning of H1, by the way? What's
OD minus R.
H1 is basically enthalpy of the vapor leaving the condenser. Sorry, going to the condenser. This is H1. Sorry, here.
We must find the latent heat of vaporization.
Yes, this is one approach. This is going to be one approach. But I know this is my V1, sir, because it's coming from first stage here. And I know the composition here, since it's total condenser. So that means Y1 and XD and X0 here are all the same. So now when I say what is the value of H1, it's a saturated vapor. So I can say basically I will have to just substitute in this equation. I don't substitute in this equation because it's vapor here. So I substitute in this equation and I put Y now is equal to XD because the composition Y1 and XD and X0 are all the same. So all I have to do is just go and say, okay, I have the equation ready, this equation. Okay, where's that equation? Here, this equation, I say H1 now means going to be at Y is equal to 0.95, okay? Is equal to 67 minus 24.9 multiplied point. What would be the value here, guys?
$34.97. 43.
Yeah, 43. Then I'm very close to this value here. As a matter of fact, should be very close to this one. So it's 43 point something. Huh? You said 0.9. Should be 0.97 or something like this. This is kilojoule per mole. Now I know H1, what I need, H0. So H0 is going to be at also X is equal to 0.95 is equal to this one, 30.48 minus 18.81 multiplied by 0.95. What would be the value here?
$12.6.
Yes, 12.6 kilojoule per mole. So now according to this equation, and I know R is equal to, from previously I know it is equal to 2.3. So what would be OD now? Can you calculate OD for me? Or if you calculate it, I think there's no need to waste time. If you do this one, if you say OD minus H1, which is 43.9, divided by 43.9 minus H0, which is 12.6, should be 2.3. Accordingly, OD should be 43.9 plus 2.3 multiplied by 43.9 minus 12.6. How much is this? If you calculate, it should be 119 or 120, something like that.
115.9.
100
15.9.
point.
9.
You sure about that? Because I have different
8,
numbers. But
9,
anyway,
yes.
115 point.
8, 9.
Okay. Okay. I have different number here. Just 43.9. Sorry, 43.9 minus 12.6 here is going to be multiplied 2.3 plus 43.9. Yeah, 0.89 here. This is kilojoule per mole. So now this is going to be almost the maximum value in my scale here. So I go back here and then start. Now I have the range here. It's up to 15. So I can say 120 maybe. Okay, or even 130 should be okay. Okay. So now if I start with let's say 120 here. Now this is H small or H capital. H small or H capital, depends. 120, I go down to 100. Come on. $100, and now this one is going to be close. Sorry for this one. This is going to be 140, 120, and here maybe 100, and here 80s. 60. This one is, it's not going to be enough, so I have to.
Doctor, we can start from 120.
Yes, you can start from 120 here, for example. And then you have 100 here. You can have here 180 here, 60, 40, but then you have 20. You can have 0 here. And you want to take into account also OW, of course. So maybe here it's going to be minus 20 and minus 40. Hopefully it will be okay. And this is going to be 140 as well. Okay. So now we have this value. H capital is going to be 67 at y is 0. So it's going to be 67 somewhere here. I can't, this is 65, 67. This is your first point. And at y is equal to 1 is going to be 42. So it's going to be somewhere here. This is 42 probably. Okay, so I can use this. And then I have for the H small, and x 0 is going to be 30 something. So it's going to be somewhere here. 30 maybe. And at x equal 1 is 11, so it's going to be somewhere here. And I use this one and just connect these two lines, or 2 points. Let's see. Connect the other lines here.
Doctor, it's enough to take for the enthalpy equation just at y equal to 0 and y equal to 1 and x
Very good
equal
question. Very good question. Why I just use 2 points? Because it's a straight line. But if it is not linear, because the relationship here is linear. So if you wanted to do a straight line, if you want to draw a straight line, you need only 2 points. But if it wasn't a straight line, then you cannot. If it was, for example, 67, let's see, 0.63 minus 24.9 y squared minus, for example, 1y, you can't take 2 points. You have to take several points. Okay, this is on because we have a straight line. So a straight line, you need only 2 points to connect them, and then it's going to be okay. Tamam. So far, so good. Now, what are the points I want to determine now? OD. Where's OD? OD is, I already determined. OD is 115. So 115. Here we go. Just a little bit here. Okay. So, but 115 is going to be, if you take this one, it's going to be at 0.9 xd, so it is going to be at, this is 0.9, it's going to 9.5, so it's 9.4, so it's going to be somewhere here. Sorry, let's do it this way. So 9.4 here is going to be here. Because Oops, be careful when you draw. You have to make sure your ruler is 100%. And it's gonna 115. So it's 115 is gonna be somewhere. So this is your line here. We will connect it to, and then we go and then try to get 115 here. This is what it says here. It's 115.8. So let's say 116. I come back to my graph and then try to rotate this one. So it's going to be 116. It's not easy. So it's somewhere here. So this is your point here. This is your OD here. And this is going to be fixed here. Now, what about this feed stage here? Where's my feed stage? Where's my feed location? Go back to the problem, and I know it says here saturated vapor. So if it is saturated vapor, that means it's going to be where it's going to be located exactly on the line of H capital here. And the composition is basically 0.5. So I come back to the same here at 0.5 here, and this is going to be my feed point here. This is my feed here. Now I have to connect to the OW. I don't have to do anything, just go and it's 0.04. So I say, okay, I know XW is 0.04. So I go to 0.04 here. This is my 0.04. Okay. And I'd say this is my 0.04. And then I take this ruler again and I try to connect the feed point with the OD point here, basically somewhere here, like this one. Try to be as accurate as possible. And I connect this line. Now my point here is going to represent what? It's going to represent OW. So now I have almost everything. All what I have to do is just go one by one, step by step, until I determine the number of stages. Any questions so far, guys? This is probably, we are at the end of this. So is it okay now? Okay, good. So now what I'll do, I say, okay, I have, this is going to represent what here, guys? It's going to represent Y1, so, which is equal to 0.95. I need to draw the tie line. So what I do, I go back to my graph here, and I say, okay, at 0.95, when my Y is 0.95, which is going to be somewhere here, this is 0.294. Yeah, it's gonna be somewhere here. تقريبا, if you are good. So let me do it. So this is not right. This is going to be for somewhere here. Somewhere here you can draw it. You can say this is my point, and then you can say, okay, at this point, this is how you're gonna do it for each point now. So that means your point here will correspond to تقريبا 0.7246, so 0.78. So I go back here, I say 0.78 to this diagram. Where's my 0.78? 0.78, this is 0.72, 0.74678. So this is going to be my other point. So this is my what? This is going to represent x1, which is 0.78, and I just connect them by this line. Okay, and that will represent the first stage here. This is the tie line. will represent the first stage. Now what I'll do, I will use OD now, and I connect it to the X1. This is my X1 here. Come to this, and I say, okay, now I connect it to this one. Here, this way. يعني تقريبا, let's be honest, I'm not good in this one. So that will give me another point here. X1, based on the design equation, will be related to OD. So we know X n and yn plus 1 and OD are connected. So I now have X1, that means I can get the one that connects these two is going to be Y2. So this one is going to be my Y2. So this is my Y2 and is equal to almost 0.84. I go back to the same thing here, to that, and I say 0.84. I use this table here. Sorry, this I got a 0.8 here. I have 0.8. 2.84 here is going to represent this one, this point here. If I use this one, this is 0.84 here. Okay, so this is my 0.82. This is my 0.84 here. Okay, and I turn this one down here. Upsy daisy, upsy daisy. Yep. So it's gonna be almost 0.685, almost 0.685 here. If we go down here, almost 0.6, because this one, it should be here. So it's not exactly here, so it should be here. 0.485. So we go back here, 0.845. Where's my 0.48 here? 0.48 here, 5, so it's going to be somewhere here. So this is my second point here. And then I'll have to connect these 2 points here together, and that will represent the other tie line. And then I connected this one. Now let me, so that will represent what? This is Y2, and this is going to be X2 here. If I connect X2 with OD, I will get the Y3. Oopsie. So this one is going to be Y3, which is almost 0.6246, 0.66. Tamam. Okay, so now this will represent stage number 2. I go back to 0.66 and get my X here. And I will do it very quickly now. 0.66, that means it's going to be somewhere here. 0.66 here. I'll do it here since it's not still have time here. 0.66, that means it's going to be somewhere here. I'll do it at this time. Sometimes it gets freezes. 246 here. Sorry about this one. So yes, it's going to be somewhere here, and this one is going to represent 1.28. So I go back to 0.28 here. Okay. 0.28 is going to be somewhere here. Okay, this is This is my second point. So I connect these two lines. And this will be number 3. And then I connect this one to still be, where's my feed? Okay, here we connect this one to this one. يعني تقريبا okay, let's freeze this here. Okay, so here we get the other point. It's very close to this feed line. This line here, you see. And then from this one, we go back to, this is going to be point, where I got this one. This one is going to represent X3 here, and this will be Y4. And Y4 here is basically 0.5, almost 2. So I go back to 0.52 here. I go to 0.52 is going to be somewhere here. So it's 0.18 here. 0.18 is going to be here. So now I connect these two lines here. Now this means this is going to be my feed stage. So this is 1, 2, 3, and this is going to be my feed stage here. Now I don't connect this one with the OD now. I have to connect it with this one. So what I do, I go here and I connect it with this one. Since I passed the okay, now sorry. So this is going to represent Y6 is equal to, sorry, Y5 here, because Y4 is going to represent feed stage, and this will be 0.4. So I go back to my equilibrium data. 0.4 will give me almost 0.12. 0.12. So I go 0.12 is going to be here. I connect these two lines together again, and that will represent the tie line. Sorry, it's not clear here, but yeah, approximately. So that will represent stage number, this is 3, 4, and this is going to be 5. And then I connect it here, sorry, with this one. I connect this point again. Okay, try to be as accurate as possible. We will try our best, but sometimes it doesn't work. Yeah, so you go, and here this is going to be your Y6 here. Y6 is 0.2, تقريبا 8 here. So if you go back, 0.28 here is going to represent 0.06 or 0.07 here, almost. 0.07, that means somewhere here. This is 0.8, 0.7, so it's going to be somewhere here. So that means your tie line is going to be between these 2 points here. And then you connect this, going to be your, we forgot to mention this one is going to be your not X feed, but feed number 4 here. Stage number 4, and this is going to be stage number X5, and this is going to be X6 here. If you connect this one with the last one, I guess that's because you can't have more than this. It's not you can, but you already reached the OW here. So basically, now that's it here, I guess. Here's going to be 0.1245. Maybe this is going to be Y7.15. If you go back to 0.15, you see 0.15 is going to represent here almost 0.4 here. So you probably reached the stage here that you are looking for, and all what you have to do, just tie line. Last tie line is going to represent the boiler, by the way. So this is going to be last tie line you're going to draw. That will be your, sorry, that will be your reboiler. It's a little bit messy, but as you can see, you can have more than what you have in the Excel sheet. So you see any deviation or any mistake, but as you can see, it's not very big difference. Any questions? So far, so good.
And Doctor,
Yes.
the stages will be the number of the tie lines or the number of the area in
the number of the
between?
tie lines. No, the number of tie lines. Each time you draw between Y1, for example, and X1, that will represent stage number 1. Between Y2 and X2 will represent stage number 2. Y3 and X3 will represent stage number 3, and so on. And the tie line that is going to cross the this line, you see you have a line between this one, this point, and this point, and the feeds. Huh? Now, the tie line that is going to cross this line will represent the feed stage. And in this case, it's going to be number 4 here, feed stage. According to my drawing, of course, it's going to be number 4. Any questions? So now if you want to, for example, you want to go back and try to solve the problem based on just McCaptail method, you can do the same thing, by the way. You can go back to here. Now, since you know the flux ratio, what you can do here, you can say, okay, that's fine. So you're going to delete all of these points here. I will do it since we still have some time. Okay, I will remove this one. There's no need for this one. There's no need for this one because we're going to have another intercept. Okay, so now what are you going to do? You will go back and say, okay, now the flux ratio is equal to what? We calculate the flux ratio is 2.3, so that means the intercept here is going to be what? Here we got it from, it's going to be XD over R plus 1. XD is 0.95 divided by R, which is 2.3 plus 1. What would be the value here? It's going to be 0.95 divided by, what is the value here? So 0.95 divided by 3.3 is equal to 0.28. So my new intercept is going to be 0.28, let's go 0.3. So it's going to be somewhere here. So now what I have to do is just draw between, sorry, this one is going to be taken off. Okay, we'll draw this line. We draw between the new intercept here, sorry, and XD. Yeah. I don't have to extend it, by the way. Why? Because I need to draw the Q line. Q line is going to be here. And I connect it to the, you know, this, where is this one? I know that it's 0.4 here, 0.2, 0.4. So this is my XW here. So I connect this one with the straight line here supposed to be. So this is my point here. So I connect this one. With this point. And that's it. You just now count the number of stages based on your equilibrium data. And then very straightforward. So you can go 1, 2, 3, 4, and then you reach 5 here. Of course, my drawing is not clear, but this is how you're going to do it. So you can say, for example, 1, 2, your feed stage now is number 3 instead of number 4, 5, and 6. So you have 5 stages because that last one is going to be your reboiler. And our calculation based on Poisson-Savarite, we find out to be 7 stages. So as you see here, the difference shouldn't be that much, even with just hand drawings. Okay. Today I will, by the way, before I forget, I will send you this, the assignment number 1. Okay, so please go and try to do it in before 1 hour time. We'll send you the first assignment, inshallah. Regarding the quiz, it's not going to be on Monday because usually we have quizzes on Wednesday. So it's going to be on Wednesday and it's going to be on chapter 7. Any other questions?
Doctor,
Yes.
if we want to get OD and we have like a table of H values, how can we do it?
OD, what do you mean OD and H values? H values, if they are
I
in
mean
the
a table instead
table
of
instead of what? OD is calculated from this equation, from this one, based on their flux ratio, based on H1 and H0. Now, maybe your question, I know what you're trying to say. Now, because when we calculated H1 and H0, we used the equation. That's probably what you mean. But if you don't have equation, if you have a data in table, simple, you draw the data like this one. You draw it first, okay, like the previous example. You draw the data first, and you come at this XD. This will give you H0 because total reflux, of course. And this, you go up here, that will give you H1, which is at Y equal XD. And this is going to be at X equal XD. You get it from the graph after you're drawing here. Okay, and then once you get these two values, you go back to this equation and you determine OD. Okay.
Okay, thank you, doctor.
Okay, guys, thank you very much, and see you inshallah next week on Wednesday, because on Monday is going to be a public holiday. Thank you very much again.